I hope you're all having a great day. I'm Mr. H. Thank you for joining me. We're continuing here with this additional technique now. We have linear differential equations of the first order, everything presented in this video, as such shown over here. If a differential equation has this specific format, you have a dy over dx, a derivative followed by something which looks like that is equal to q. This right here represents a differential equation which has a linear format. There's a specific way of solving this differential equation, and this requires two specific procedures. One is you have to find an integration factor. That integration factor is determined by a procedure such as this: e to the exponent integral p dx. What is this p? It represents the coefficient of this y. If you're given a differential equation, you write it out in this format and it looks like something like this, then that coefficient falls here. The integral of that in terms of that e exponential base then helps you determine the integration factor, because when you solve this out you get your integration factor. That integration factor is necessary for this procedure. Once you have determined your integration factor, you have to multiply both sides of this equation around the equal sign with that integration factor, and then you come up with a new expression. From that new expression, then this right here is another important step. Right here, the integration factor determination was one important step. Then this is your next important step. You have to find some sort of a function or an expression that is in fact represented by its derivative on the left side of that equation. What does that mean? You'll see it very well when we're looking at our examples, but roughly, once you've multiplied the integration factor by this part, it will give you some sort of expression, but that expression was derived by implicit differentiation from something. Something over here, by means of implicit differentiation, gave you this. What is this item right over here? And that right there is what you have to determine. There are two determinations, this and then this right here. Your function that is represented by the derivative. All of this might seem a little bit overwhelming, but trust me, it's not hard once you look at one or two examples. Let this be our first question. We have dy over dx plus 3y equals e exponent 4x. You know it's looking very much like that format I was showing you, like this. That's exactly what it looks like, and that's exactly how you have to view it. You have a p. The coefficient of p over here is this right here, 3. You have to find your integration factor. What is this integration factor? It's determined by this e integral p dx. But that right there is e integral p, which is 3 dx. What's the integral of 3? It's 3x. You're going to get e to the 3x. This right here is your integration factor, which will multiply with everything you see over here. You'll do dy over dx plus 3y is equal to e to the 4x. You multiply it by your integration factor, e to the 3x. When you multiply it across, it's not hard. Just distribute it across. You have e to the 3x dy over dx plus 3y e to the 3x is equal to e to the 7x. The determination of this integration factor is your first hard part of this technique. Now, the determination of the function which gave you this derivative is your second hard part for these type of question. What was that function over here or expression for which if you did the implicit differentiation you'd get all of this? And you have to figure it out. It would require you to do some sort of backwards thinking here, or do like reverse thinking. You're thinking backwards, like what was the expression if you did the differentiation of it, you'd end up with this. With a little time and practice you can develop that technique, and your answer would be y e to the 3x. Why would this be the case? Because if you did the derivative of this expression, implicit differentiation using the product rule, I can work it out for you. You'll have e to the 3x d or dy y dy over dx plus, remember the product rule template? You'll have y times the derivative of e to the 3x. I'll erase this momentarily, but you'll see from here you'll have e to the 3x dy over dx, because the derivative of y is just a 1. But from here you'll have 3y e to the 3x, and this is exactly what you wanted, and that's exactly what it is. So what was that factor over here which gave you this derivative? It's exactly this right over here. And that right there will substitute for everything you see over there. And you have to do this reverse thinking, or reverse engineering as you want to call it, to come up with that. And that right there is usually a hard part of these questions. Now you can rewrite everything with this new substitution. This substitutes for this. You're really looking at d over dx y e to the 3x is equal to e to the 7x. Now you integrate it with respect to x. When you do the integral and the derivative, they cancel out. You're really looking at y e to the 3x is equal to just the integral of this. You're just looking at the integral of this, which you know is e to the 7x over 7 plus c. But you can solve for y and take e to the 3x on the other side. You'll have e to the 7x divided by 7e to the 3x plus c over e to the 3x. And if you want, you can clean this out and write a good answer. You'll have e to the 4x over 7 plus ce to the minus 3x. This right here, along with this y, represents the function or the expression for which this differential equation is true, and it would be right. Again, remember in these questions, this determination of the integration factor is hard, and the determination of this expression which gave you this derivative on the left hand side is the hard part. We will look at 2 more examples in this particular video just to help us along with what we're seeing over here. Our question is this: tan x dy over dx plus y equals secant x. It looks very familiar in terms of presentation to this basic form, which is this py is equal to q. There's only one problem here. We have a function with respect to that dy over dx. We don't have any coefficient here, but here we do. But if you were to divide everything here by tan x, you can eliminate it and then make it look exactly like that form. And you would end up having here dy over dx plus, you see this tan x in terms of its reciprocal, you can just write cotan xy. Nothing wrong with doing that, is equal to secant x over tan x. Can be simplified, and let's simplify it. It's really 1 over cosine is equal to sine over cosine. These cancel out and you're really looking at a cosecant x. All of that simplifies to cosecant x, and you can put that right there. Nothing wrong with doing that. Now we have to find the integration factor. Integration factor is always determined from e to the integral p dx. But what exactly is p? P is this, cotan x. E integral cotan x dx. What is the antiderivative of cotan x? Well, isn't it natural log sine x? And these are the instances where you're determining the integration factor. You never put this c. I didn't do it in the previous example, and I won't do it here. You don't do it at all. You don't need to do it, because you're using this only to determine your integration factor. But this right here is no different than you looking at e to the ln x, which you know by means of a logarithmic identity is always equal to x. Well, then this right here is equal to sine x, because these will cancel out by means of a procedure I'm not showing you, but you know that by means of a identity. You could do y equals all of this and then bring in the natural logs and do all of that computation. You'll be left with nothing but sine x. So your integration factor here is not e exponent ln sine x, is just sine x. This sine x will now has to multiply with everything over here. You'll have a sine x dy over dx plus, what's cotan x and sine x? It's cosine x, is equal to 1. Now you have to find the expression or the function for which this represents the derivative, and with a little practice you can determine it. And that item will be nothing here other than you're looking here at a y sine x. If you do the derivative of this implicit differentiation, you'll have exactly this by means of the product rule. So that's exactly what you will substitute here. You're looking at a d over dx y sine x is equal to 1. Now do the integral of all of this. This right here is just a y sine x, but this right here is an x plus c. Therefore, y is equal to x plus c over sine x. This can be your answer, final answer. You can do it right that way, or you can work it out some more. You can do cosecant x plus cosecant x c, and then you can actually, if you want here, you can just isolate cosecant x and then you can do x plus c, and that right there can be another way of expressing the same thing. But this right here is fine. This here is a good answer. Even some would say that this right here is an answer too. Y sine x is equal to x plus c, and you could stop right there. And for our last question, we're looking at this: x dy over dx plus y equals x sine x. It almost looks like that, but it isn't, because you have a coefficient here which you can eliminate and then make it look like that. You'll have a dy over dx plus 1 over xy is equal to sine x. Now it looks certainly like that, and this right here represents your p. Remember, to determine your integration factor, you're doing p dx, the integral of that, but you're really looking at an integral of 1 over x dx. But the integral of 1 over x is easy. You're looking at e to the ln x, and you know this by means of logarithmic identity is equal to x. If there's any hesitation why that is the case, allow me to just show you. Y is equal to e ln x. ln y is equal to ln x ln e. Then ln y minus ln x is equal to 0. You have y over x under a common log is equal to 0. Y over x is equal to e to the 0, which is equal to 1, and then y is equal to x right here. And that's exactly why that is the case. The integration factor over here is just x. This integration factor is multiplied across. both sides. You'll have a x dy over dx plus y is equal to x sine x. Now you have to find the expression or the function for which this represents a derivative, and it's not hard. You just look at it and you're really looking at d over dx. You're looking here at an xy. If you do the derivative of this by means of product rule implicitly derived, you'll get this, and that's exactly what you have. You have a d over dx xy is equal to x sine x. You're doing the integral of this, you're doing the integral of this, but this cancels out. Here you have to do integrating by parts, so that's going to take a little bit of work. Integration by parts, and I'll do it for you. And what we can do is just bring in the answer. We'll work it out here. U is equal to x, du is equal to dx, v is equal to integral of sine x dx, which is minus cosine x. Then you do uv minus integral v du, right? Uv minus integral v du. Bring everything into play. V here is minus cosine x, u is an x, and then minus integral v du minus cosine x dx. When you clean out all of this, you're getting a minus x cosine x plus integral of cosine x, which is just a sine x plus c. This will come and place itself right over here after this integration procedure would have been done, and I'm gonna put it for you. You would have been looking here at xy was equal to all of this, minus x cosine x plus sine x plus c. If you want, you can stop right here. If you want, you don't have to progress further, but you can. You can write it as sine x minus x cosine x plus c. It's up to you, but this right here is a good final answer. Or you can just take the x on the other side and divide everything by x. You'll have a minus cosine x plus sine x over x plus c over x. This is another good answer here with regards specifically to y is equal to everything else. So this right here represents the expression or the function, these two, for which this differential equation is true, and the question has been solved. Again, I will repeat, the determination of these integration factors is the harder part, and the determination of the derivative for which this part, the left hand side of the equation, is represented, that's the other hard part. And those are the single two hard parts for these type of questions. Everything else follows easily if the integral over here is easy to determine, because this can be a little bit of a hang up for some students as well. But that's it for this video. Thank you for watching. Have a great day. Bye.